So before starting today's class, I will advertise it's a seminar by Professor Fang. So actually he's working on the computer architecture field, and he's associate professor at UC Riverside, University of California, Riverside. Then he wrote very good papers, good research papers, and he published very good research papers on the conference. So actually the topic of the talk is the general purpose processing on AI and ML, machine learning accelerators. So I think this topic is very important topic recently because we use accelerators recently. Okay. So you are learning about the CPU architecture, right? But recently the AI applications are very critical, and then we use GPUs. GPUs are developed for accelerating graphics applications, but we use GPUs for accelerating parallel applications, right? So that's why we use GPUs for AI and machine learning applications. So also, Google developed their own accelerators called the TPU, and it's the tensor processing unit. So actually many software or hardware companies are developing their own accelerators. So it is because the AI applications are very popular, and then we need to increase the performance of these applications of computer systems. That's why we are focusing on the accelerator architecture. So we are also focusing on the domain-specific architectures such as the GPUs. GPUs are also kind of domain-specific processors. So I think this seminar is very so this seminar is very good seminar. So if you are available, then you can tell them. So actually, this is the CSO colloquium course. So I invited him to this course, and then also you can attend this talk. So everyone can attend this talk, even though they do not take this course, the colloquium course. So okay, but this is seminar time, and then also you can visit the 애기는 생활관 302. Okay. Yeah. So some announcement, and then okay, let's go back to our journey, our journey on memory system. Okay, so we have 3 classes left, and then so you can enjoy it in the break after the final exam. Okay, so in the previous class we learned about the associative caching, right? So why do we use associative caching? Because if we use the direct map cache, then actually the many blocks. So actually the cache size is limited, and then many memory blocks. So actually many memory blocks are mapped to the same cache block, right? The direct map cache. But in the direct map cache, in the direct map cache, we can just store one cache block per set. So this is set. So which means that if some 2 blocks are mapped to this one cache set, and then if these 2 blocks are also frequently used, but A and B are evicted because A and B are mapped to the same stack. So in this case, so even though the cache has the available empty spaces, these empty spaces cannot be utilized. So the cache miss rate can be increased. So we use the associative cache because in the associative cache, in the one cache set, we can store multiple cache blocks, right? So which means that for this case, the A and B can be stored in the cache. So this is the associative cache. But the associative cache is more expensive, so which means that we need to use more hardware resources to implement the associative caches. But the performance can be improved. Also, I also explain about the performance by cache associativity, right? So we don't need to use the fully associative cache. So it's because the cache miss rate. So usually for general purpose applications, and I also mentioned usually the cache miss rate is saturated by cache associativity. Okay, so that's why we don't need to use the fully associative cache. Okay, that's what we learned, and then this is the structure architecture of set four-way set associative cache. Okay. Okay. So and then we can just consider the replacement policy because so there are multiple blocks in the target cache set, and then if this target cache set is already full, and then new blocks need to be allocated, then one of valid blocks need to be evicted from the cache. And then because there are multiple blocks, we need to select. We need to select the cache block to be evicted, right? Because there are multiple blocks. So we frequently use list recently used, right? So it means that this is the meaning. Okay? The list recently used. So the list recently accessed. It's the same meaning actually. So the cache block, if the cache block is accessed a very long time ago, then this block is evicted. The oldestly accessed. Okay, you mean the oldest accessed, not old block. Okay, it depends on the access time. So access time, okay, not some allocated time. Okay, so and then but LRU, so this is called the LRU replacement policy because this is the least recently used. So actually, if we use the two-way set associative caches or four-way set associative caches, the LRU is rather simple. So we can implement the LRU easily using the simple hardware. But if the set associativity is increased, like the 8-way or 16-way, then the LRU is it's a rather difficult. It's rather difficult to implement LRU policy, right? So in this case, we can use the random replacement policy. So, but the performance, so we can, so random replacement policy does not consider the cache access time, right? So sometimes the random replacement policy may using the random replacement policy, the cache evicts the frequently accessed block. So it can be possible, right? Because it's just random, right? Randomly the blocks are evicted. But if the way is the test set associative is increased, then the performance of random replacement is becomes similar to the performance of LRU. Okay, so sometimes we can use the random replacement policy. So for example, ARM processors employ random replacement policy for their caches. Okay. Okay. Let's consider about the multi-level cache. So if you see the memory hierarchy, the pyramid shape, so you can find the caches here. This is the register file, and this is the main memory, and then you can find the cache between register file and main memory. But also you can find that you can find the L1, L2, L3 in the cache hierarchy level. Okay. So it means that the caches are also organized hierarchically. So it means that we can use the L1 cache. So this is the highest level cache. And then also I mentioned that we split the L1 cache to the L1 instruction cache and then L1 data cache, right? And then after that, there can be lower level cache, okay, like the L2. So L2 is the lower level cache, it's a lower level. So it is because L2 is located underneath the L1 cache, right? So this is the lower level cache. And after that, there can be L3 caches. So modern processors, modern CPUs typically include the L3 caches until the L3 cache. So this is also lower level cache. So usually this L3 cache is called the last level cache. So LLC, last level cache. So then what is the purpose of this cache hierarchy? So cache is the small cache space is smaller than the main memory, but we can just store the frequently used data in the cache. Why? Because we want to use the best memory, best cache, but best memory, right? But the problem is that we want to store more data in the cache because the main memory is very slow, it's too slow. So we want to store more data in the cache. The problem is that if we increase the size of the cache, then cache access latency is also increasing. So you can just think like this. If the memory size is large, then the memory is slower. Okay. So for the error cache, we want to use the fast cache for the error cache, right? So which means that the error cache size needs to be small. Okay, then we can use the fast cache. But we want to also store more data in the cache. So we can add the larger cache. So L2 cache. So L2 cache is lower than L1 cache, but the size is larger. Okay. So that is the purpose of multi-level cache. So we can store more data, but we can store more data the slower L2 cache. Okay. So some high-end systems. So actually the most laptop or desktop CPUs includes the L3 caches, the last level caches. So this is the example. So it's the multi-level cache example. It's the CPU-based CPI is the one. So it means that this is the ideal CPI. Okay, so the every data access is cache hit. And then clock rate is the 4 gigahertz, and then miss rate per instruction is the 2%. The main memory access time is the 100 nanoseconds. So the main memory access cycle, the cycle is the 400 cycles, right? Because the clock rate is the 4 gigahertz. Then what is the miss penalty? So this cache looks like this. The L1 is here, L1, and then after that, there is the main memory. So if the request is missed in the cache, it's an L1 cache, then this request is given to the main memory. So which means that the miss penalty is the same to the latency, access latency of the main memory. This is the 400 cycles. Then what is the effective CPI? So this is the CPI for the ideal cache. So 1, and then we can add the additional cycles by these penalties. So and then this rate per instruction is the 2%. So 0.02 multiplied by its penalty. So it's 9. So in this configuration, the CPI, if we just consider the cache misses, then CPI is increased to the 9. So this is the multi-level cache example. So let us assume that we can add the L2 cache, and then access time is the 5 nanoseconds. So actually, I do not mention the access time of the L1 cache, but we assume that the access time of the L1 cache is the same to the clock period, right? So it's 0.25 nanosecond. Okay. So compared to the 0.25 nanosecond, so you can find that the access latency of L2 cache is it's higher, right? So it's very high. And then the global miss rate, but this is the global miss rate to the main memory. The global miss rate to the main memory is the 0.5%. Okay, so which means that this is the percentage that access the main memory, right? Percentage of requests that access main memory. Okay, the 0.5%. Because we have L2 cache, then the L2 cache size is larger than the L1 cache size. So the miss rate is reduced. So in this example, the miss rate of L1 cache is the 2%, so which means that 2% of instruction generate the request to main memory, right? But this is just assumption. So if we just add the L1 cache, then the global miss rate, the miss rate is reduced to the 0.5%. Then let's calculate the performance by multi-level cache organization. So what is the penalty? Okay. So in this configuration, this is the L1 cache, and then there is L2 cache, and then after that there is the main memory, right? So if the request is given to the L1 cache, and then if this request is missed in the cache, then the request is given to the L2 cache. So this request needs to access L2 cache, right? Then what is the penalty of this missed penalty of L1? And then if we assume that if this missed request are hit in the L2, then the missed penalty is the 20 cycles because the access life is the 5 nanoseconds, right? And then also, this is the cache. So the request can be hit or miss, right? Then the addition, the missed request in and two also access main memory. So this is the extra penalty that access that is required for accessing main memory. So what is the CPI? CPI, this is the ideal CPI, and then this is the additional is penalty, which penalty required for accessing L2, and then this is the additional penalty which is required for accessing main memory. Okay. Then is it because the global miss rate is reduced, and then also the miss penalty is reduced by L2 cache, the CPI is decreased to the 3.4. So performance ratio compared to this configuration. So the performance is increased by 2.6 times, right? So this is the impact of L2, the multi-level cache. So we require multi-level cache because the error test size is small. Okay? So which means that we require the larger L2 cache. So primary cache, this is the error cache. So when we implement CPUs, then we can just organize the cache also hierarchically, like L1, L2, and L3. Okay. The primary cache, this is the error cache. We just focus on minimum hit time for implementing error cache. Okay. So hit time is critical for L1. So that's why we cannot increase the size of L1. But L2 cache, when we implement L2 cache, we focus on low miss rate. Okay. So because the error size is small, the miss rate can be high. So if there is no L2, then the miss request access main memory. So this, so you know, in the previous example, we can observe the performance degradation is very high, right? So, but by adding L2 cache, we can decrease the miss rate, which means that the L2, because the L2 can store the more data. Okay, so which means that we can avoid main memory accesses. So this is very important. So you know, so I mentioned the main memory is extremely slow. So which means that if possible, we need to reduce the number of accesses to main memory. So this is very important for the performance of computer systems, right? So why do we use L2? We want to reduce the miss rate. We want to avoid accesses to main memory. Okay. So primary cache error, we just focus on heat time, the access time, but L2, we just focus on the lower miss rate. Okay. So this is the benefit of by multi-level cache. But so I skip here because we did not learn about the out-of-order processor architecture. Okay. But when we implement an application, then we can consider the cache size. Okay, so which means that the performance, the performance of a cache, like the cache hit rate or cache miss rate, can be also influenced by software, okay? Software implementation. Okay, so it is because the software requires data, right? Data. But if the software can store small part of data frequently, and then this frequently used data can be found in the cache, then we can increase the performance of this software. So, which means that when we implement a software, then we can design the, the software. We can make the software access small part of data, even though the software requires a large amount of data, and then for some time period, then we can make software focus on small part of data, a small partition of data. Okay. Then this small partition of data can be stored in the cache, and then we can reduce the data access time. It's very important. So we can increase the performance. So the example. So I believe everyone knows about the matrix multiplication, like MM. Matrix multiplication, like A multiplied by B. Okay. So, and then, the recently, the matrix multiplication is very important. So, because the MM operations are frequently used by AI applications or the ENN, the neural network applications. So this is very critical. But what is the matrix? So matrix actually includes the multi-dimensional elements. So for example, 2D matrix includes the n by n elements, right? Okay, it's a 2D matrix. So, the matrix multiplication, such as the A multiplied by B. So for this operation, then we just multiplication like the dot product of the row of A and then column of B, right? So which means that, for this element, then we need to access the all rows of this row of the wizard matrix. We need to access the all elements of the matrix A. But we can just use the one column of matrix B, right? So, which means that if the matrix size is very large, then it cannot store all elements in the cache. This is the problem. So for example, actually for the next row, then we also need to access these elements of matrix A again, but these elements are not found in the cache if the matrix size is very large. Okay, this is the problem. So if the matrix size is very large, then we cannot utilize cache in the CPU. Then, how can we improve the algorithm? We can improve the matrix multiplication algorithm by using submatrix. So which means that the large matrix A is split into the smaller submatrices. And then matrix multiplications can be performed using these multiple submatrices. That is the how the matrix multiplication can be implemented for considering cache. Okay, this is actually the very important matrix multiplication algorithm, right? So by splitting the large matrix into the smaller sub matrices, then we can store the elements of smaller sub matrix in the cache. And then these elements can be frequently found in the cache. Okay. So this is the result. So if you see this result, so as you can see, this is the 950 by 950 matrix multiplication. So this number represents the matrix size. Okay. So, and then this is the unoptimized version. So this is very naive version. Okay? So it's the normal matrix multiplication. And then this is the blocked matrix multiplication. So which means that the large matrix is split into multiple sub-matrices. Okay? So, and then this is the performance. The floats, so which means the floating operation per second. Okay? The performance. We can just understand this is the performance. So for the unoptimized version, if the matrix size is increased, then we can observe that the performance is degraded dramatically, right? Why? Because of cache. Okay? This large matrix cannot be stored in the cache. And then, which means that we cannot utilize the data locality in the cache, right? This is very critical problem, actually, in the modern computer systems, right? Because so popular applications, the modern applications handle a large amount of data, and so which means it's a big data, right? So we cannot store this data, the large amount of data in cache, which means that we cannot utilize the data locality of these applications. It's very hard. Okay? Which means we need to design the optimized algorithm for processing the large data. Okay? So if you see the block matrix multiplication, so this is the optimized version, but as you can see, the performance is degraded, but the performance is higher than the unoptimized version. Why? Because we can utilize the data locality. And then, because the size of sub-matrix is smaller than the original matrix, then the elements in this matrix can be stored in the cache. And we can reduce the data access time. It's very critical, right? So compared to the if we just compare the 960 by 960 matrix multiplication, then here, so you can find that the performance is nearly double for the block matrix multiplication. So, this is very critical, right? So the point is that when we design an application, then we also need to consider the memory hierarchy. Okay? So this is also very critical for the performance of the application. Okay. A summary of cache. So memory hierarchy. So why do we use the memory hierarchy? Because we want to exploit data locality. Okay, and then we also want to use fast memory, the large memory. But this memory is we cannot use the this perfect memory because so we need to implement the memory hierarchy. Okay, and then so for the block placement, we learned about the associative cache, like the direct method cache, and then n-way set associative cache, and then fully associative cache. Okay. So direct method cache is sent to the one-way set associated cache, which means that we can store one cache block per set. This is the direct method cache. Then n-way set associated cache means that we can store up to n cache blocks per set. Okay, this is the n-way set associated cache. And then fully associated cache, we can store we can allocate new cache blocks the same on any location of the cache. This is the fully associative cache. And then higher associativity. Higher associativity reduces this latency. Okay, but this is the advantage of higher associativity. But this advantage is complexity, cost, and access time. Okay, this is the pros and cons. Okay, so this is how to find a block, and then also you can find the comparators, number of comparators required for implementing the direct method cache, and then n-way set associated cache and fully associated cache. Then for the cache replacement, we can use the LRU. We frequently use the LRU. Then we can also use the random. Okay, this is just the random. Okay. Write policy. There can be two write policies for the write hit case, write true and write them. Okay. And then this is, so I want to explain about this is source of mislead. So this is called the 3 C's of cache. 3 C. Why? Because as you can see, the class of cache misses starts with C. So the compulsory miss, and then capacity missing, and then conflict missing. So 3 C's of cache explain explain why cache miss occurs in the cache. Okay, so we can classify the source of cache misses using 3 C's, like compulsory or cold, or capacity or conflict missing. Then, what is the compulsory missing? Compulsory missing. So it is also called the cold missing. So compulsory missing means, so firstly, the cache is empty, right? Or cache is empty, or if a certain block is not accessed, then this block does not exist in the cache, right? Because the data block is not requested. Then this block exists in the main memory only. We cannot find this block in the cache. So if the target block is requested for the first time, then it's already missed, right? So this type of miss is called compulsory miss, compulsory miss, or cold miss, and cold miss. So it is because the block is firstly requested. But we need to distinguish this case. So for example, so let us assume that, so this is the for loop, the for I equals 0, I is less than 100, and I plus plus. So this is the iterative loop, and then sum is accumulated at the array I. Okay, then so let us assume that this array is if array is requested firstly by this loop, right? Firstly by this loop, then what is, and then we already know that if so we the 100 elements of this array is are requested, right? By this in this example. Do you understand? Okay. Then what is the number of holes? So I mentioned that the array element is requested for the first time, right? Then so we already know that the 100 elements are requested. Okay. Then what is the number of holes this is in this case? Yeah. 100? 100? Actually not. So I mentioned that we need to distinguish this case. So actually what number of cold misses is not 100 for this case. Why? We already know that the array element is firstly requested by this statement, right? And then this statement will be executed 100 times. Then by definition of the code means the compulsory means we can expect that the number of code misses is equivalent to 100. But it's not true, right? Because cache block size it can be large. So what does that mean? In a single cache block, this cache block may include multiple elements, right? So in the example, in the example, we can find that cache block size is 16 bytes. So in this case, one cache block includes 4 integer data, right? Because if we assume that the size of an integer is 4 bytes, then this single cache block can include 4 integer data, right? Then this is the array, so which means that in a single cache block, if the size is the 4 byte, then array 0 is here, array 1 is here, array 2 is here, array 3 is here, right? In a single cache block. So when the array when the array 0 is requested by this statement, then this is cache miss, and then it is also called miss, right? The firstly is array is requested. For this miss, entire cache block is allocated in the cache, right? And then after that, array 1 will be requested by this program, right? But we can find the array 1 in the cache because the elements from array 0 to array 3 are already allocated in the cache. Array 2 is the same, array 3 is the same. But what does that mean? Even though array 0, array 1, array 2, and array 3 are requested for the first time, because the cache block size is large, we can find array 1, array 2, array 3 in the cold miss is not 100 for this case. The number of cold misses is 25. You understand? So we need to distinguish the firstly requested data and then the miss in the cache or the coordinates. Okay? Then how can we reduce coordinates? If we increase the size of a cache block, then we can reduce number of cold misses, right? So this is very important actually. Then what is the capacity missing? So capacity missing means that because the cache has the limited space, and then because of this limited capacity, the miss rate can be increased. So this is the capacity missing. Okay, which means that we can, if we increase the cache size, we can reduce the capacity missing. Okay. Then how can we measure the capacity misses? So how can you measure this cold misses? So we can measure cold misses like the cache size is infinite. We can assume that the cache size is infinite, and then we can run the application, and then we can measure the number of misses. Okay, and this means cold misses. Because the cache size is infinite, then we can just observe cold misses, the infinite cache. But if the cache size is limited size, then we can also measure the capacity misses. So we can measure the capacity misses like this. So firstly, we can count the number of misses of infinite cache, and then we can also count the number of misses of finite cache. So it means that the cache size is limited. Then which will be larger? This will be larger. So the difference between the number of misses of infinite cache and the number of misses of finite cache is the capacity misses. So this means the cache miss by limited cache size. Okay, this is the capacity misses. And then what is the complete misses? So we can also expect the misses by cache organization. We already learned that the fully associative cache exhibit the lower miss rate compared to the direct mapped cache. So the miss rate is also influenced by cache associativity. So complete miss means that complete miss represents the cache misses. Cache misses due to the limited associativity, right? This is the conflict miss. So how can you measure the conflict misses? We can measure the number of misses by fully associative cache, and then number of misses by target cache. Okay, because and then this cache is not a fully associative cache. Then the miscount of this cash will be larger, right? So if we just calculate the difference between the miscount by fully associated with cash and then miscount by some target cashes, then we can measure the complete misses, number of complete misses. Okay, so these are called the 3 states of cash. Then we can use the 3 states of cash to classify, to analyze the source of cash miss. Okay, okay. So this is some cash design trade-off. So which means that we can just change the cache organization or cache configurations, right? And then this table explains the impact by different cache configurations. So firstly, we can increase the cache size enough to reduce capacity misses, right? So in fact, we can decrease capacity misses. Then what is the disadvantage? Cache size is increased. Then access latency is also increased because the memory size is increased, then memory performance can be decreased. So this is the benefit. There is the pros. This is the cons. Okay. So if we can increase the capacity misses, but the may increase the access time. This is the heat time. Okay. So also we can increase cache associativity. So by increasing cache associativity, we can decrease conflict misses, right? But we may increase access time, block size. As I mentioned, if we increase the block size, we can decrease compulsory misses, the cold misses, right? As I mentioned, I also exhibit the example. But miss penalty is increased, and then also the cache miss rate can be also increased. Okay, because the caches are occupied by some large blocks, and then this is called the cache pollution. Okay, cache space is occupied by some large blocks. Okay, this is called the cache pollution. Okay, so you can find the pros and cons here. So this is also very important. Okay, so cache is done. So now, we can use the virtual memory. So what is the virtual memory? So what is the opposite concept of virtual? What is the virtual? So what is the virtual? So we can frequently hear the terminology of virtual reality. And what does that mean? Virtual is actually, it's fake. It's not real. Okay. Then what is the virtual memory? So we are learning about the memory system, right? And then I mentioned that the data is stored in the memory component. Then what is virtual? Fake memory. Then what is the opposite concept of virtual? So actually you can frequently experience the virtual and some other concept in the computer science field. The opposite concept is the physical. Physical means the real in the computer systems. Then what does that mean? So we are learning about the computer hardware. So I mentioned that the hardware is real, right? But virtual memory, it's a fake memory, right? So also you can understand like, so usually the software is virtual, then hardware is physical. The hardware is real, and the software is actually working on the fantasy world. Okay, it's a virtual world. Why? So think like this. This is your computer, okay, and then actually our computer runs many applications simultaneously. So concurrently at the same time, we can run many applications. But is that possible? It's not actually possible. Why? The CPU has the limited number of cores, and then actually usually one core can run one application, one thread. Actually, it's a thread. It's called the thread or process. But if we just click Ctrl+Del and then 잘 깔리자, you can find that many processes. So these processes are actually running. But what does that mean? So even though the computer system has one main memory space, but we can just run many applications. So many applications are allocated in the memory space, and then operating system just run one of these applications, one of these applications using CPU core. Do you understand? So actually, the many applications are running. So which means that operating system just generate the memory space, generate some. So in order to run a certain application, the required data and instructions need to be stored in the main memory, right? So instructions are also data, right? So actually, many applications are occupying this physical memory, main memory, DRAM, and then operating system selects the one application among these launched application, and then only this one application is assigned to a certain core, right? But if there are multiple cores, multiple threads can be assigned to the cores simultaneously or concurrently, right? But for one core, we can just run one thread. Okay. Then what's the problem? Think like this. So in chapter 2, we learned that this is our high-level language code. Okay. And then I can compile I compile this high-level language code, and then we just generate the machine code. Okay, and then machine code also includes the load instruction, load word A. Okay, for example, load word A. But even though it's the same binary, we can execute the same binary codes multiple. We can just launch same binaries multiple times. It can be possible, right? So it's the same binary code, and then same binary codes can be executed concurrently. What's the problem? So for example, we can launch Microsoft Word, and then we can again launch another Microsoft Word again and again, right? We can launch multiple Microsoft Word, right? What's the problem? Problem is, oh, it's the same binary, and then load word A. So this binary execute the load word A, and then this binary also execute the same load word A. Problem is, even though these binaries may require the different data, but because the instruction is the same, then if the same load word is executed, then same data is loaded. But we need to avoid this case, right? Even though the binary is the same, these binaries may require different data, actually different data, because these are different processes, or different threads. Okay? But same instruction, same load instructions are just executed using the address A. So we can just identify data using addresses, right? So which means, oh, the A is requested by this binary, and then A is also requested by this binary. But I mentioned that we need to avoid this case. Okay, so this is actually very difficult topic. Okay, and then this is called the memory management. Okay, it is because the computer systems need to run many applications, multiple applications at the same time. But sometimes the address can be the same, so we cannot actually this case cannot be managed. Load A. We cannot manage this cases using software. Okay, because so it is like this. So it's the same binary. The same binary can be executed on the computer A or computer B or computer C, but the running environments are different. Okay, we cannot. We don't know. We don't know some actual real environment of the execution environment of this application. Okay. Then how can we avoid this case? So we can avoid this case like this is the load word A, and then load word A is the same, but we can think this A is the virtual address. Okay, so virtual address means that this address is accessed by software, but actually in the physical memory, then this data is located in the different physical memory, different physical address. Okay, so it means, so it's the same virtual address, like load word A, but using the different translation table. This is translation table. This address is changed to the physical address. So it's a real address in the physical memory. Okay, so physical address A, and then physical address B. So it's the software just handles virtual address, okay, in the virtual memory field, but is virtual address, but we also store the data in the memory, in the real physical memory, in the real space. Okay, because the data is real, right? So when the disk address, this data is used by on software, actually the virtual address is translated into the physical address. And then using this physical address, we access the main memory. Then, because even though the virtual address is the same by the same binary, it can be the same for the different binaries, but the physical address is different, like A or B. So actually, the different threads can you access the different data. Okay. So this is the concept of virtual memory. Okay. So software just can access memory space using virtual address, but actually actual data is stored in the physical memory. So I mentioned that the physical is real. In the physical memory, using the physical address. And then for this operation, we require the translation between virtual address to this is translation between virtual address to physical address. Okay, so this is the concept of virtual memory. But so actually, another benefit of virtual memory is that the software engineers do not need to consider about the limited physical memory space. What does that mean? Okay. So I mentioned that in the hardware, the data is stored in the physical memory. Okay. So the data is stored in the physical memory, but the size of physical memory differs by hardware system. Varies by the hardware system, right? Because some computers includes the 4 gigabyte of memory, and then some computer includes 8 gigabyte of memory. The memory size is different, but the software is the same. The binary code is the same. Then how can we handle this case? So actually, if the memory space is large, then we can just improve the performance of software, right? But the memory size varies by computer systems. Then how about the software engineers? So how can handle this case, this situation by software engineers? So if the software engineers need to handle this cases, this situation, then software engineers may need to generate the different versions of software. So the version A is for the 4 gigabyte of memory, version B is for the 8 gigabyte of memory, C is for the 12 gigabyte of memory. So different versions. So many versions. This is a very cumbersome, right? It's not good, right? But another important point is that, as I mentioned, actually we run many applications concurrently in the computer system. So we don't know the actual situation of software execution, right? So actually, software engineers just assume that, oh, computer systems have nearly infinite memory, the very large sized memory. For example, like 16 terabytes of memory. The virtual memory is fake. But the software engineers can think like this, the virtual, right? And then also the software engineers think that, oh, we can use the core resources anytime. Okay? But for the memory space, the software engineers think that, oh, the computer system has very large sized memory. Okay? Then they write the code. But we already know that the computer systems have limited sized memory. The physical memory size is limited, like 4 gigabytes or 8 gigabytes. Then how can you handle this case? 4 giga or 8 giga. Even though software just handle large size of memory, a certain data can be stored in this physical memory. And then remaining data can be stored in the storage. Okay? So what I want to say is that the software engineers just play in the virtual world, so virtual memory space. The very large, we assume that there is very large memory in the computer system. We do not consider any physical limitations, any physical organization of the computer system. We just assume that this is the virtually provided memory space. Okay? But this size is very large, but physical memory size is limited. So actually, a certain data is stored in the physical memory, but a certain data is located in the storage because the storage size is large compared to the main memory. Okay, the storage size is also limited, but we assume that the storage also certain data can be stored in the storage, right? So what does that mean? We can use this physical memory like cache. Okay? The software engineer think that, oh, our data, my data can exist in this large sized memory, large sized main memory, but actually the computer systems have different sized physical memory. Also, the physical memory size is a little smaller than some required data. Okay, sometimes. Then we can use this physical memory like cache. It means software just access this large size data, but using the translation, as I mentioned, the virtual address needs to be translated into the physical address. Using the translation, some data is stored in this physical memory, the real DRAM, but some data is stored in the storage. This is another concept of virtual memory. Okay, so it means we can use physical memory, real physical memory, as cache of the virtual memory space. So actually, this is the original purpose of virtual memory. So actually, in the old computer systems have very small sized DRAM. So DRAM is very expensive. So we can use this expensive DRAM like cache. So actually, this is the main purpose of virtual memory. But so recently, the DRAM size is very large, so we don't need to use DRAM like the cache, but we still need to use the virtual memory. It is because as I mentioned, the memory space needs to be managed. So memory spaces need to be allocated to many running applications, many running threads or processes. Okay, for this management, we need to use the virtual address to physical address translation. Okay, so this is virtual memory. So this is another difficult part because we are still running, playing in the virtual and real physical world. Okay. Okay. So I stop here, and then in the next class we will deeply dive into the virtual memory. 감사합니다.